I am Sara Cravanzola from the University of Torino, and I would like to present you my work about carbon-based piezoresistive polymer fibers. Okay. So in these last years, composite polymer materials with electrical properties for structural and sensing application have gained a great importance. And this is why we focused about composite materials based on conducting nanofillers and polymers. These kind of materials are made up of two phases. The first one is a matrix, and this is a polymer which has no conductive properties and which gives to the final composite properties of resistance to corrosion, the fact to be easy to process and to be lightweight. Then the second phase is a filler, for example, carbon nanotubes, graphenes, or graphite nanoplatelets. They are conductive and they give to the final composite property of electrical conductivity because of the formation of a conducting network of the filler within the polymer matrix. So we realize a conductive and piezoresistive metal-free polymer fiber which properties mainly depend on the nature and the concentration of the filler. So it is very important to know how much filler I have to put in the composite to have an electrical conductivity. So it is important to define the percolation threshold of my composite, which is the lowest fraction of the conducting filler at which the composite begins to show electrical properties. So it is the percolation threshold is a specific concentration of the conducting filler at which we can see an insulator to conductor transition because of the formation of this continuous conducting network. An important property of this kind of composite is piezoresistivity, which is the change in electrical resistivity under a mechanical deformation. And so during this mechanical deformation, there is a modification of the conductive network of the filler, and so the composite shows a change in electrical conductivity. So we can say that for this kind of composites, the electrical conductivity is stress-strain dependent, and this is very important for sensing deformations. And this is why these kind of composites can be applied in fields such as polymer and flexible electronics or sensory application. So in our composites, we use the polypropylene as polymer matrix and multi-wall carbon nanotubes and or graphite nanoplatelets as filler. And for prepare the composite, we use the melt mixing method and then extrusion. And we realized the fibers that you can see in the picture. And these fibers were characterized by X-ray diffraction. And here you can see the patterns. The first pattern is about the pure polypropylene fiber. And here you can see that there are narrow peaks which emerge from a very broad feature, which refers to the amorphous phase of the polypropylene. And these peaks reveal the presence of two phases of the polypropylene, the alpha and the beta phases. Then the third pattern refers to the composite containing only graphite nanoplatelet, and the fourth one refers to the fiber containing both the nanofillers. So we have both multi-wall carbon nanotubes and graphite nanoplatelets. Here you can see the presence of the peaks of polypropylene and another peak at 26.5 degrees. There you can see in the inset, and this peak is due to the diffraction of the 002 plane of the graphite. Then finally the second pattern refers to the composite which contains only multi-wall carbon nanotubes, and here there is no peak at 26.5 degrees, probably because the quantity of multi-wall carbon nanotube is very low, it's about 2% by weight, and because the crystallinity of this kind of multi-wall carbon nanotubes is very low if it is compared to the crystallinity of the graphite nanoplatelet we used. So knowing the peak at 26.5 degrees, we applied the Scherer equation and we tried to evaluate the thickness of graphite platelets, which is about 25 nanometers, and this value is very close to the thickness of pure graphite nanoplatelets. So the fibers, okay, the graphite these composites were analyzed from the electrical conductivity point of view, and we found out that only the fibers containing both multiple carbon nanotubes and graphite nanoplatelets were conductive. So this composite was analyzed in such a way to see if the extrusion rate applied during the extrusion phase and the diameter of the fiber could influence the electrical resistance of the composite. And we found out that yes, they influence the electrical resistance, and in particular with a higher extrusion rate and decrease in the diameter, we have an rise in the electrical resistance. So the composite containing both multiple carbon nanotubes and graphite nanoplatelet was analyzed by scanning, electron microscopy, and atomic force microscopy. But first of all, we applied a technique which is a non-conventional scanning electron microscopy. It is called low potential SEM. In this technique, the acceleration voltage of the electron is very low, and detecting the secondary electrons, we were able to obtain the images on your right, which are charge contrast images. Here, bright areas corresponds to conductive areas of the samples, while dark areas corresponds to non-conductive areas of the sample. And so we can say that we have realized, we have obtained conductivity maps of our samples. And so with these images we can see which is the distribution of the conductive fillers within the matrix. And so we try to see with this technique fibers which were obtained with different extrusion rates and with different diameters, and we discovered that the extrusion rate and the diameters affected the distribution of the conducting fillers within the matrix. And the most conductive fibers is the one with a large area, with a large bright area where there's a large aggregation of conducting filler. Then this conducting area was analyzed by conventional SEM and AFM. And in these areas there is the presence of both multiple carbon nanotubes and graphite nanoplatelets. In the SEM image, the multiple carbon nanotubes are highlighted by dotted lines, and we can see that multiple carbon nanotubes can help the formation of the conductive network, bridging the graphite nanoplatelets, the adjacent graphite nanoplatelets. And so we can say that in these composites there is a synergy between multi-walled carbon nanotubes and graphite nanoplatelets in enhancing the conductivity of these composites. Then the composite containing both multiple carbon nanotubes and graphite nanoplatelets were analyzed to see if they are piezoresistive. So a fiber, as it is, was subjected to a cyclic deformation, in particular to a tensile loading. And after that, a same kind of fiber was embedded in a polypropylene panel to create a sensor, a piezoresistive sensor. And this panel was subjected to cyclic deflections. And then here you can see how the loading, the elongation for the fiber, and the deflection for the panel, and the resistance change during the deformations. And as you can see, when a load is applied, the resistance changes. So we can say that these composites are piezoresistive. And another thing to say is that the change in resistance is proportional to the applied load. And as I said before, the conductivity of these composites mainly depend on the presence of aggregation of contacts between the nanofillers. So we can say that during the elongation there is a modification of the conducting network with the loss of contacts between the nanofiller, and so there is a change in the resistance. So as applying an elongation, there is a change in the applied load, so in the stress of our composite, and a change in the resistance. We can say that there is a relation between piezoresistive properties of this composite and stress strain. Then, in this kind of composite, I used as filler graphite nanoplatelet, but we thought that it could be interested to use exfoliating material, for example, so graphene, to enhance the electrical conductivity of these kind of composites. So, we try to obtain graphene from graphite nanoplatelet by ultrasonication. So we ultrasonicated the graphite nanoplatelets for 1 hour in isopropanol, and the dispersion obtained was analyzed with AFM, and here you have an image. The platelet, and here you can see the profile of the platelet of the image. Its height is about 0.4 nanometers, which is very close to the d-spacing of graphite. So we can say that in this image we have almost one layer graphene. Then the same dispersion was analyzed by UV visible spectroscopy, and we have a band at 270 nanometers, which is due to pi-pi star transitions of conjugated carbon bonds. And this value is very close to the value we found in literature for synthesized graphene. But this work is still in progress. This is all what we do about exfoliation of graphene. So conclusions. Polypropylene fibers with piezoresistive properties have been prepared by adding nanocarbon conducting fillers, multi-wall carbon nanotubes, or graphite nanoplatelets. We can say that the extrusion rate and the diameter of the fibers affect the electrical properties of the composite, and by monitoring the changes in electrical resistance of each fiber which is embedded in the panel compared to an initial value, it is possible to evaluate the effect of an applied loading under the deformation of the sensor. So integrating two piezoresistive fibers into two sandwiched polypropylene panels, a piezoresistive sensor device has been made, and graphene obtained from exfoliation of graphite nanoplatelet can increase the electrical conductivity of the composite. Thank you for your attention.
Thank you. So, time for questions.
Thank you for the nice report. And the question is, if you add a very big amount of carbon nanotubes, like maybe 20%, I did not understand why you say that only carbon nanotubes did not give you some conductivity. It means that there is no percolation between tubes, or why they...
Okay, because we use both carbon nanotubes and graphite nanoplatelets. So.
But if you will use only carbon nanotubes and make a huge concentration, will you obtain some conductivity? Or?
Because didn't want to use, because we started with preparing composites containing only graphite nanoplatelet. Then then we prepared them and we measured the electrical conductivity, and then we extruded them to obtain fibers. But we discovered that a composite, a conductive composite, after extrusion was no more conducting, because the extrusion rate, the temperature affect the electrical conductivity. And so, and it was for a quantity of graphite nanoplatelet around 15%, which was a great volume to insert in the matrix. And so it was impossible to use a higher concentration of graphite nanoplatelet. So we thought to use carbon nanotubes and to see if they could help in enhancing the electrical conductivity, and they do so.
Okay, thank you.
What is the size of your graphite?
Okay, graphite nanoplatelets, the thickness is about from 25 nanometers to 30 nanometers, which corresponds to a number of layers that goes to 60 to 90.
All right. So if there are no more questions, thanks again.